Welcome. I'm Yusuf Yazıcı. Today talk will be approaches to fraud detection on credit card transactions using artificial intelligence and machine learning methods. It's a paper written in a format of survey, examining the papers about this subject between 2018 and 2020. So the content will be the first, a brief introduction, and the approaches, what approaches are used using machine learning methods. And there are some common challenges that we'll briefly talk about. And also we will talk about the conclusion, and we will finish, hopefully. So nowadays, for the last years, most of the shopping transactions are gone through with the credit cards or debit cards. We don't use any cash anymore, most of us. And of course, this is an advantage, but some of people, the fraudsters, uses this advantage to convert this into a disadvantage. Then of course, there could be some fraudulent transactions. These fraudulent transactions cost $2.17 billion yearly. That's a huge number for the industry. And then, of course, with this huge number, there are some approaches to detect them. The old approaches uses rule-based ones that mainly focus on the business part of the industry or the bank, and write some algorithms, rule-based algorithms. Then in the conclusion part, there's a decision that whether a transaction is fraud or not. And the modern approaches uses AI-based one, machine learning or artificial intelligence, and they mostly use again this data and let the algorithms learn the data and extract the features from the data, and therefore provides a probability whether a transaction is fraud or not. And the AI-based one can be categorized into three parts: supervised, unsupervised, and semi-supervised learning ones. And we will briefly talk about them. And in this presentation, we will try to talk about the state-of-the-art approaches. And there are, of course, some common problems almost every paper experience. The problems are feature engineering problems because the data is very limited, taken from the bank or industry. And of course, most of the transactions are legitimate transactions that are not so much fraud compared to the legitimate ones. There's of course, there's a big problem for the machine learning problems, imbalance data set problem. And of course, the real time, there are some challenges with try to predict the fraud transactions in real time rather than offline. And we will talk about them later. So we said that there are some approaches, supervised and unsupervised. How is a supervised learning algorithm works? It is basically when we have a labeled data, for example, we label the data as fraud or legitimate, and we use some machine learning algorithms, and the machine learning algorithm actually, right, like in the picture, tries to state a function here. For example, the algorithm here found this function, this linear function. The function actually separates the data into two parts. In our case, for example, these could be fraud ones, these could be legitimate ones. And this is actually happens because the supervised learning algorithms learn the labeled data, and in the next part, tries to predict whether the transaction, the classification is something or any other thing. In the supervised learning approach, we don't have any labeled data here. We just have some data that we don't know their label, their target beforehand. The unsupervised learning approaches, for example, sorry. For example, clustering just draws a line, draws a circle, line, whatever it can find, and tries to separate, tries to cluster the data based on how they are close to each other. Unsupervised learning generally does this. And of course, there is this third approach, a semi-supervised learning approach, that combines supervised and unsupervised learning methods. And that method we can use when we have much of our data is unlabeled, but we have some little labeled data, and we combine supervised and unsupervised learning approaches there. This table examines how the papers written between 2018 and 2020 is are structured based on their algorithm use, whether they use a real data set or not, whether they derive the features, derive the limited features and use other features there, and how are they categorized based on the evaluation metrics. Because there are so much evaluation metrics going on there, and each paper tries to find a new right evaluation metrics to increase their score. The most common used algorithms here are decision tree algorithms, random forest algorithms, random forest classifier, or the modern artificial neural network algorithms are used here. And of course, SVMs, logistic regression, k-means are also used, but their weight are not very high compared to other ones. And we will talk about some common algorithms here. And of course, there are some evaluation metrics, right, like precision or recall, or under the area under the curve metrics. We will talk about them later. The common algorithms are decision trees, as I said, random forest classifier and artificial neural networks. And the evaluation metrics are precision. We can state the most common used ones as precision, recall, F1 score, or economic efficiency. The economic efficiency is a special part of specialized to do this problem, this monetary problem that use how much money is spent in that transaction. And the precision recall F1 score is used almost in every machine learning problem. So there is no accuracy score here, right? Why don't we use any accuracy score? Because as we mentioned earlier, most of the transactions are legitimate. So we could just, without a machine learning algorithm, we could just guess that the transaction is legitimate, and 99% of the time we will be right because this imbalanced data set problem. So here in this chart, false negatives are very important. So here the raw line, the green and red ones, that these are fraudulent transactions. Really, they are fraudulent. And the true positive ones, the green ones, they are fraudulent, and we predicted them as fraudulent transactions. And the false negative ones, we predicted as they are legitimate, but actually they are fraud. That's a huge metric for the banks and industry, because when we predicted as legitimate, but they are actually fraud, the money are gone, and really banks and industry lost so much money out of that. So we really need to find this metric, find the false negative rate here. And the precision and recall metrics are really important here. And we can say that recall, for example, is the false negatives derived by the sum of true positive and false negatives here. And the precision is again, true positives divided by the sum of true positive and false positive. And F1 score is also used here because precision and recall are both important. F1 score uses the harmonic mean of precision and recall score and give a weighted precision and recall weighted score. It's a very good evaluation metric. And also, as we said, there is an economic efficiency metric that we talk later. So we will briefly talk about these decision trees, random forest classifier, and artificial neural networks algorithms. Decision trees ask some question based on a tree and tries to, at the bottom of the tree, it tries to classify, it tries to give a probability whether a transaction, whether data belongs to some class or another class or any other class. For example, in this fraud detection scenario, it could ask, the first question will be, could be asking to ask place, whether place is supermarket or bank or any other institution. So whether it's a supermarket, it could ask the gender, the sex of the individual. For it is a man, it asks any other question. It is a woman, it asks any other question. Whether it is a bank, for example, it could ask the education. It is whether it is undergraduate or junior or high school, etc. And by asking this question with a tree format, it eventually gives a classification. In random forest classifier, on the other hand, it uses this and decision trees. In decision trees, we have just one decision tree, but in random forest classifier, we have and decision trees. And each decision tree here independently gets a classification, there's a probability. And at the end, for example, in this tree 1, it's classified class A, tree 2, class B, 3, and etc. class B. And at the end, there's a majority voting here, and that's eventually predicted as the final class, whatever it is. And the modern artificial neural networks, it's like a black box that could be example in how our brain works. It's an input. We provide some input, and it could finalize it as an output with a nonlinear function, giving its probability. And at the inside, there are some hidden layers that could find the weighted. There's a weighted matrix that could calculate it with matrix multiplication. And then when we come to the end, there's a back propagation processes that uses some mathematical operations to increase their performance with evaluation metrics. The W weight matrix is very crucial in artificial neural networks. So with economic efficiency, Sa et al. Summarizes this with this functionality. Economic efficiency equals to the sum of the transactions with returns function. What is this returns function? It is the sum of the legitimate transactions. There's an if condition here. If it is a legitimate transactions, it is just use this the upper formula. What is VI and K? K here is it represents the percentage that the company retains per transaction. For example, it could be 3%. For with per transaction, we could just say that they gain 3% of the money. And this V is the actual amount. And here, if it is legitimate, it is true negative that we predicted as legitimate and it outcomes as legitimate. It's a gain for us, but the gain is very little. It is 3% times the amount. But if it is a fraudulent one, it is false negative. It is 1 minus K. It is 97% times the amount, and it is minus sign. That gives us a negative score, negative efficiency score. The penalization is very high here, and that evaluation metrics could be quite handy. And this is not enough. There is an EE relative score that uses max and mean economic efficiency scores. EE max could be defined as the algorithm predicted every classification as true correctly, and EE mean is every classification is misclassified. Every prediction is misclassified. So EE relative here is EE min minus EE real divided by EE max minus EE real. That could be a very an efficient economic efficiency evaluation matrix that could be used in fraud detection algorithms with machine learning. And the second part of the presentation here talk about the common challenges. There are three common challenges that we want to talk about. The first one is imbalanced data set. The second one is feature engineering, and the third one real-time working scenarios. In imbalanced data set, as we mentioned earlier, most of the transactions are legitimate ones, and it is very, very hard for machine learning methods to detect the fraudulent ones. In the feature engineering, right, the poor transaction information extracted from the bank or any other industry, the organization database, is quite restricted. There is only time, credit limit, transaction amount, maybe the place could be used, but not much. And these are very limited features, and we maybe there's a probability that we could not predict the fraud transactions. So we need to make serious feature engineering here. And also, the fraud detection scenarios are, most of them are offline. We make a transaction, we make a shopping, the money is taken with our credit card, and maybe 1 hour or 2 hours later, maybe 1 day later, we get a call that our transaction is fraud, came out as fraud. That's I think it's ridiculous. And nowadays, real-time working scenarios workings are in the researchers area. They utilize some frameworks, for example, Spark, Kafka, Cassandra, to effectively process data. And right after the transaction, there's a possibility that the outcome could be it is legitimate or fraudulent. And of course, there are some of them use Hadoop to effectively format the data in HDFS format. So in the imbalanced data set problem, we could give the information of the number of legitimate transactions per day in 2017 completed by Tier 1 issuers, the first class issuers, is 5.7 million. Whereas the fraud transactions in the same category is 1,150. The rate here is 0.02%. This is very, very less. So the problem arises here, and there are some, of course, solutions for these common problems. The first one is oversampling the minority class or undersampling the majority class. We could oversample the fraud transactions, and of course, we could undersample the legitimate transactions here. And as we talked about, there are some cost-sensitive loss functions. This approach, this loss functions also helps to reduce to imbalanced data set problem. And some papers talk about some interesting approaches to, for example, Fiore et al. They use an approach of increasing the number of interesting but underrepresented instances in the training set using generative adversarial networks. This is the brand of deep learning architecture, and it is very modern nowadays. A lot of resources use GANs today, and Fiore et al. Also uses this to actually this could be defined as an oversampling, but with using GANs. And Retire et al., for example, uses random forest classifier to select only relevant features. Here, there is a machine learning algorithm use only extract the relevant features, and this could help imbalanced data set problem. And there is an algorithm called SMOTE, SMOTE, a synthetic minority oversampling technique. That is a famous algorithm that uses an oversampling approach. And of course, Zhu et al. Uses weighted extreme learning machine for assigning different weight to different types of samples. That could also reduce the imbalanced dataset problem. In the feature engineering part, there are some solutions, of course, because there are limited data in our hand taken from bank or industries. The first one would be extracting features from distinct groups of transactions, sharing data that shares same characteristics. It is called homogeneity-oriented behavior analysis. So we have time in our hands. We could extract some really good features with that time. We could extract, for example, whether it's a weekday or holiday. The difference between each transaction could be also crucial here, and the mean or standard deviation could be used per transaction with time, for example. And another approach could be some approaches uses deep learning algorithms. They prefer to not doing anything because they claim that deep learning algorithms already extracts the features themselves, and we don't need to waste time with feature engineering, and we need to focus on the actual algorithm part. So doing nothing could be a choice here. And some approaches, some researchers learn from fraudsters online. They follow the news or industry experts to learn to extract some new features. And there are some new features like frequency of transaction per month, or there are some, of course, dummy variables. We could fill them. And an interesting one would be extract the location part, because the actual location of the transaction could be very important. For example, whether it's a restaurant, gas station, or any other place, and whether a transaction amount in a given retailer is greater than 10%. That could be a retailer-based approach. That could be very handy. And with these feature engineering approaches, the evaluation metric score would be increased drastically. And of course, the third part of the challenges is real-time working problems. Some papers, for example, Carcilla et al. Utilizes Apache Spark, Kafka, and Cassandra to effectively process the data. And they use an algorithm called SCARF, real-time fraud detector, called scalable real-time fraud finder. And they claim that they process 200 transactions per second, and it is it is much more. They claim it's much more than 2.4 transactions per second that belongs to their partner. And some approaches uses Hadoop, for example, to encode data in HDFS format. And they use Patil et al. Uses SAS system to convert the file into a RAW data, and with that way, the raw data can be transferred to the analytical model effectively and in a very fast way to build the data model. And as a conclusion, we try to present how machine learning and artificial intelligence methods are utilized to detect credit card frauds. And we try to mention the common challenges like feature engineering, imbalanced data sets, and real-time working problems. And lastly, we could say that the common challenges, the first two common challenges, feature engineering and imbalanced data set, are much more examined throughout the papers, but real-time working scenarios I think are not ready yet. That could be the next approaches that we use in our papers, maybe, and in the next time. Thank you for listening to me. That was all. Thank you for this awesome conference.